In this video, we shall look at ideal gas law. This law relates states of a gas. The states in question are pressure, measured in Pascal, volume, measured in cubic meter, and temperature, measured in the units of Kelvin. We shall also look at various special cases of this ideal gas law, such as Boyle's law and Charles' law. We will then solve a few problems based on these concepts. Let's look at the following model. In a volume V, you have a sample of gas inside right there, and these gas molecules exert certain amount of pressure P Pascal, and this entire sample of gas is at temperature T Kelvin. Let's assume that the sample of gas is an ideal gas. So it will obey the following equation. PV equals N R T. P is the pressure of this gas in Pascal. V is the volume occupied by this gas in the unit of cubic meter. T is the temperature of that gas sample in the units of Kelvin. In addition to that, N is the number of moles of this gas sample, and this R is called universal gas constant with a value of 8.314 in the units of joules per mole per Kelvin. So this value of R have same value for all gases, at least at sufficiently high temperatures and low pressures. So by definition, an ideal gas is one for which this equation right there holds precisely for all pressures and temperatures. This is an idealized model, and it works best at very low pressures and high temperatures, when the gas molecules are far apart and in rapid motion. Now, although there is no such thing in nature as a truly ideal gas, all real gases approach the ideal state at low enough densities. Let's look at a special case of this equation right there. Now let's assume that we hold the temperature T and the amount of substance represented by number of moles constant. And let's say we compress the gas so as to decrease the volume from V1 to V2. The question is, what happens to the pressure? From the ideal gas equation, we know the right-hand side of this equation is a constant. So that means the product PV has to be a constant. Or we say the pressure is inversely proportional to the volume. So if we decrease the volume, say from V1 to V2, now the pressure will go up from P1 to P2. So as the volume goes down, the pressure goes up. This is known as the Boyle's law. Likewise, if I increase the volume of the sample of gas from V1 to V2, as shown by this diagram, then the pressure will go down. This inverse relationship between pressure and volume at constant T and number of moles can be represented in a following graph. So this is a PV graph, and the graph would look like that to denote the inverse relationship between P and V. Next case is, let's maintain the value of pressure and the number of mole of gas, and we shall change the volume and see what happens to temperature. So in this case, the initial volume of the sample of gas is V1, and we expand the gas so its volume becomes V2. The pressure is maintained as P, respectively, and we do not change the number of moles of the gas. The question is, what is the new temperature T2 of this sample of gas? Again, from this equation, we see that when P, N, and R is obviously a constant, V, the volume of the gas, will vary in proportionate manner with temperature. So that means the ratio of V over T is a constant. So in this particular case, as we increase the volume of this gas sample from V1 to V2, what's going to happen to the temperature? It will change from T1 and to T2, and the value of the temperature will also increase. Likewise, if I decrease the volume of the sample of gas from V1 to V2, the new temperature, T2, will also become smaller compared to the original temperature, T1. This law is known as the Charles law. And the graph representing Charles law will look like this. It's going to be a straight line, denoting V is proportional to T. Next, if I were to fix the volume and the number of moles of the gas, and now changing the pressure and the temperature of the gas sample, let's say initially the pressure is P1, I change the pressure to P2, then the temperature would also change accordingly from T1 to T2. If the pressure is increased from P1 to P2, then the temperature would increase from T1 to T2 accordingly, and vice versa. So this relationship can be written in a following manner. P is proportional to the temperature T, or the ratio P over T can be written as a constant. And if we were to graph this relationship, we will end up with a straight line signifying the linear relationship between pressure and temperature. Then all the other variables, such as the volume and the number of moles of the gas sample, is held constant. The third special case is when we allow all pressure, volume, and temperature to change, but holding the number of mole to be constant. So in state 1, let's say the pressure of the gas sample is P1, the volume of the gas sample is V1, and the temperature of this gas sample is T1. And in state 2, we change the pressure to P2, say the volume changes to V2, and the temperature changes to T2. So the ideal gas law obviously states the following ratio is a constant, meaning the pressure, volume, and temperature of the two states can be related in the following manner. P1 V1 over T1 equals P2 V2 over T2. Let's look at the first problem. A tank contains 10 liters of oxygen at 22 degrees Celsius and 12 atm of pressure. If the temperature is raised to 30 degrees and the volume is reduced to 8 liters, find the final pressure of the gas in atm. Assume that the gas is ideal. And of course, we are assuming that the number of moles for this sample of oxygen is held constant. Since all the variables are changing, meaning the pressure is changing, the volume is changing, and the temperature is changing, so we shall use the third special case, meaning P1 V1 over T1 equals P2 V2 over T2. So in state 1, we know that the pressure is 12 atm, so that is 12. We can simply use atm. We don't have to change that into Pascal because the common multiplier when the conversion takes place will just get cancelled between the left-hand side of the equation and the right-hand side of the equation. So you can just stick with atm, and the same goes for the volume, liter. You don't have to change that into cubic meter. So the initial volume is 10 liter. The temperature, however, need to be changed to Kelvin, because when you change from Celsius to Kelvin, it is not a common multiplier anymore. You have to add 273. So you have to change the temperature to Kelvin. Now the right-hand side, the new pressure, we don't know. That's what we want to determine. Whatever it is, it will come out in atm. The volume is 8 liters. That's a new volume. And the temperature is 30 degrees Celsius, so you have to change that into Kelvin. So whenever we use this equation, the temperature must be in Kelvin. And solving for P2, you will get 15.4 ADM as the answer, and that solves the problem. Problem 2. Assemble a gas with volume 950 cubic cm at 38 degrees Celsius and 1.01 times 10 to the power 5 Pascal. Expands until its volume is 1400 cubic cm and its pressure is 1.06 times 10 to the power 5 Pascal. Now first find the number of moles of the gas present and then the final temperature of the gas sample. The number of moles can be figured out from the ideal gas equation. Now we can use the first set. The pressure is 1.01 times 10 to the power 5 Pascal, right there. The volume now is 950. Now you have to change that into cubic meter. So that's going to be 950 times 10 to the power minus 6 because we are interested in the moles. And we don't know. R is 8.314 and the temperature is 38 degrees Celsius. So you have to change that into Kelvin. And we can solve for the number of moles. And when you do that, you get 0.037 moles for the number of moles. To determine the final temperature, we use the similar equation that we used in a previous problem. P1V1 over T1 equals P2V2 over T2. Now we know for the first set, pressure is 1.01 times 10 to the power 5 Pascal. The volume can be expressed in cubic cm. You don't have to change that into cubic meter because it involves ratio now. The temperature is 38. Do not forget to change into Kelvin. And then the second state, P2, is 1.06 times 10 to the power 5 Pascal. The new volume is 1400. So 1400 cubic cm. And the temperature is what we want to determine, T2. And solving for T2 in Kelvin, you will get 481 Kelvin, or quite simply 208 degrees Celsius. And that solves the problem. Problem 3. The total lung volume for a typical person is 6 liters. A person fills her or his lung with an air at an absolute pressure of 1 atm. Then, holding the breath, the person compresses his or her chest cavity, decreasing the lung volume to 5.5 liter. What is the pressure of the air in the lungs? Assume the temperature is held constant. So here we are dealing with Boyle's law. So P1V1 equals P2V2 because the temperature is held constant. So the initial pressure is 1 atm. Initial volume is 6 liters. The pressure at the end we don't know. And the final volume is 5.5 liter. And we can solve for the final pressure in a unit of ADM, and that will turn out to be 1.09 ADM, and that solves the problem. Again, note we don't have to change liters to cubic meter or ADM to Pascal because all the common multiplier for the conversion of unit will get cancelled because they appear on both sides of the equation. Problem 4. The gas inside a balloon will always have a pressure nearly equal to atmospheric pressure, since that is the pressure applied to the outside of the balloon. Now you fill a balloon up with an ideal gas to a volume of 0.8 liter and temperature 25 degrees Celsius. What is the volume of the balloon if you cool it to 77 Kelvin? So the pressure is held constant, so we are dealing with Charles' law. V1 over T1 equals V2 over T2. Initial volume is 0.8 liter. Initial temperature is 25 Celsius. You need to change that to Kelvin. And the final volume is what you want to determine. And the final temperature is 77 Kelvin. And you can solve for V2 in the units of liter. And that's going to be 0.207 liter. And that solves the problem. Thanks for watching.